Imagine a power plant that never experiences night, never has a cloudy day, never shuts down, never dims, never stops. A power plant that generates electricity 24 hours a day, 365 days a year, at full strength, forever. There is only one place in the universe where such a thing can exist. Not on Earth, above it, in space. For over 50 years, this has been one of the great dreams of energy science. Build a solar power station in orbit where the sun always shines and beam that energy down to the ground without a single wire. The idea is old. It first appeared in science fiction in a short story written by the legendary author Isaac Asimov back in 1941, which imagined the station beaming energy across space. Then, in 1968, an American engineer named Peter Glaser turned it into a serious scientific proposal. NASA and the US Department of Energy studied it intensely in the 1970s. They ran the numbers, they designed concepts, and they concluded that yes, in principle it could work, and then they largely shelved it, because the cost of launching that much material into space was astronomically high, and the technology to beam the power was nowhere near ready. It sounds like pure science fiction, and for decades that is essentially what it remained. A beautiful idea, proven possible on paper, that nobody could actually afford or engineer into reality. China just took one of the biggest steps toward making it real. In a lab in the city of Xian, on a tower 75 meters tall, Chinese engineers just did something that brings this 50-year-old dream startlingly close to reality. And if they succeed at full scale, it could change the future of energy itself. Stay with me, because to understand why this is such a big deal, you first have to understand why solar power on the ground, as good as it is, will always be fighting with one hand tied behind its back. Think about a solar panel here on Earth. Even the best one, on the sunniest day, faces a series of unavoidable problems. First, the night. For roughly half of every day, it produces nothing at all. Second, the weather. A passing cloud, a storm, a grey winter sky, all of it cuts the power dramatically. And third, something most people never think about, the atmosphere itself. Our atmosphere is wonderful, it keeps us alive. But it is also a filter. Before sunlight ever reaches a solar panel on the ground, it has to pass through 100 kilometers of air, dust, water vapor, and cloud. And all of that scatters and absorbs a huge amount of the sun's energy along the way. By the time sunlight reaches the ground, it has lost a significant part of its original power. So a solar panel on Earth is trying to do its job through a dirty window, for only part of the day, whenever the weather allows. It is a miracle it works as well as it does, but it is fundamentally limited by where it sits, on the ground, under the sky. Now take that exact same solar panel and move it into space. Everything changes. In orbit, above the atmosphere, there is no night in the way we experience it. A satellite in the right orbit can be bathed in sunlight almost constantly. There is no weather, no clouds, no storms, no seasons. And most importantly, there is no atmosphere in the way. The sunlight hitting a solar panel in space is raw, full strength, and uninterrupted. The difference is enormous. A solar panel in orbit can collect, by some estimates, 6 times, even more than 10 times the energy of the same panel on the ground over the course of a year. Think about what that multiplier means. One panel in space can do the work of 6 or even 10 panels on the ground. It is the difference between sipping through a straw and drinking from a fire hose. And it runs all the time. A ground solar farm sits idle every night and underperforms every cloudy day and weakens every winter. A space array in the right orbit just keeps going, hour after hour, through what would be night on the surface below it, delivering a steady, uninterrupted flow. The sun in space is a vastly richer and vastly more reliable resource than the sun on the ground, simply because nothing is getting in the way and nothing ever switches it off. So the appeal is obvious. If we could put a giant solar array in orbit, it could generate clean power continuously, day and night, rain or shine, at a strength no ground-based panel could ever match. This is why the dream has refused to die for over 50 years. But there has always been one gigantic problem standing in the way. A problem so hard it kept this idea locked in the realm of science fiction. And that problem is not collecting the energy, it is getting it down to Earth. Think about it. Your solar power station is in orbit, hundreds or even tens of thousands of kilometers above the ground. How do you get the electricity from up there down to a city down here. You obviously cannot run a cable that long, so how do you move enormous amounts of energy across the vacuum of space, through the atmosphere, and down to a specific point on the ground without any wire connecting them at all? The answer in theory has been known for a long time. You do it with microwaves. Here is the concept. The solar station in orbit collects sunlight and turns it into electricity, just like a normal solar panel. But then, instead of sending that electricity down a wire, it converts the electricity into microwaves. These are the same kind of waves your microwave oven uses to heat food, and the same kind that carry your phone signals, a form of invisible radio energy. The station beams these microwaves down through the atmosphere in a focused beam. On the ground, a large receiving station, essentially a giant specialized antenna, catches the microwave beam and converts it back into ordinary electricity, which then flows into the power grid. Sunlight becomes electricity, electricity becomes a microwave beam, the beam travels down to Earth and becomes electricity again. Power beamed wirelessly from space. Now, I know what you might be thinking. A powerful beam of microwave energy fired from space sounds alarming. But the design is not a death ray. The beam is spread out and relatively low in intensity at the surface, and the receiving stations are enormous precisely so the energy is diffuse. This is about steady power transfer, not a weapon. It is much closer to a gentle, invisible rain of energy than a burning laser. But knowing the theory and actually doing it are two completely different things. And the doing is monstrously difficult. Getting all of this to work, converting the energy efficiently, aiming a beam with perfect precision across a vast distance and hitting a target has stopped every previous attempt from becoming real. For 50 years, this last step, the wireless transmission, has been the wall that everyone crashed into. And that is exactly the wall China just broke through. The project is called Zhuri, which translates beautifully as chasing the sun. It has been in development for years, led by a senior engineer named Duan Baoyan at Xidian University in the city of Xian. And rather than trying to build the whole thing in space immediately, which would be impossibly expensive and risky, the team did something clever. They built a full version of the entire system on the ground first to prove every single step works. They constructed a tower 75 meters tall, and on that tower, they ran the complete chain of the process, start to finish. They captured solar energy. They converted it to electricity. They converted that electricity into microwaves. They beamed those microwaves across a distance, and they caught them at the other end and turned them back into usable power. The entire concept demonstrated in full right here on the ground. And the results they achieved are what make this a genuine breakthrough. The system successfully transmitted over 1,100 watts of power across a distance of more than 100 meters, more than a kilowatt, beamed wirelessly and caught at the far end. But the raw power is not even the most impressive part. The most impressive part is the precision. They achieved a beam collection efficiency of around 88%. That means the microwave beam stayed remarkably tight and focused across that entire distance with very little of the energy spilling away and being lost. Keeping a beam that concentrated over such a distance is one of the hardest parts of the entire challenge, and they did it. To put this in historical context, this is not the first time anyone has beam powered by microwave. Back in 1975, NASA's Jet Propulsion Laboratory ran a famous experiment that achieved even higher efficiency. But there is a crucial difference. That old NASA test beamed power between two fixed stationary points under tightly controlled conditions. What the Chinese team did was far harder in one specific way. They tracked and powered targets that were moving. And that single capability, holding a beam steady on something in motion, is the difference between a laboratory curiosity and a system that could actually work in the constant motion of space. And then they did something even harder. They proved they could hit a moving target. In one test, they beamed power to a drone that was flying through the air at 30 kilometers per hour and successfully delivered stable power to it while it was in motion. Think about how difficult that is. Not just aiming a precise beam at a fixed point, but tracking a moving object and keeping the beam locked onto it as it moves. This is exactly the skill you would need in space, where satellites and stations are constantly moving relative to one another. And there was one more crucial achievement. The system demonstrated what is called one-to-many transmission. A single transmitter was able to send power to multiple targets at once. Instead of one station powering one thing, you could have one station in orbit acting as a central power hub, wirelessly charging many different satellites and spacecraft around it. That last idea points to what may be the first real use of this technology, and it is not what you might expect. Before it ever powers a single home on Earth, this technology could transform how things work in space itself. Consider the problem satellites face right now. Many small satellites in low orbit can only generate power from their own solar panels for about 60 minutes out of every 90-minute orbit. For the other 30 minutes, they pass through the Earth's shadow and they have to run entirely on their onboard batteries. Their whole design is limited by this constant cycle of charge and drain. Now imagine a central power station in orbit that could wirelessly beam energy to all of those satellites, keeping them charged continuously. It would be like a gas station or a charging station floating in space, topping up every satellite around it. Satellites would no longer need to carry such large, heavy solar panels and batteries. They could be smaller, lighter, cheaper, and far more capable, dedicating their weight and space to their actual mission instead of to power. And it goes further than satellites. The same wireless power could one day supply energy to a base on the moon, which endures 2 weeks of darkness at a time, or to rovers and equipment operating in permanently shadowed craters where solar panels are useless. It could power drones on Earth that stay aloft for weeks without landing. This technology, this ability to send power precisely to a moving point without any wire, has uses that reach far beyond a single power station. A single orbital power hub could revolutionize the entire satellite industry, long before the technology ever sends a watt of power down to a city on the ground. Now let me be honest and balanced, because this is a genuine breakthrough, but it is absolutely not a finished technology, and pretending otherwise would be a lie. The first and biggest caveat is efficiency. The overall end-to-end efficiency of this ground test, from the electricity that went in to the usable power that came out, was around 20%. That means roughly 4/5 of the energy was lost along the way. For a system whose entire selling point is capturing more energy, losing 80% of it in transmission is a serious hurdle that must be dramatically improved. The second caveat is scale, and this is the truly staggering part. This was a demonstration over 100 meters from a tower. A real space solar power station would need to beam energy from an orbit potentially 36,000 kilometers above the Earth. That is not 100 meters, that is tens of thousands of kilometers. The engineering leap from one to the other is almost unimaginably large. And the third caveat is construction. A full-scale station would be gigantic, with a solar array and an antenna up to a kilometer wide. You cannot launch something that size in one piece. It would have to be carried up in hundreds of separate launches and assembled in orbit piece by piece by robots and machines in the hostile environment of space. This has never been attempted at anything close to this scale. So this is not a power station that will beaming energy to your home next year or even the next decade. The roadmap is long and it is worth seeing just how staged it is. China has laid out a series of careful steps. First, a small test satellite in orbit, generating around 10 kilowatts, planned for roughly 2028 just to prove the beaming works from space at all. Then a 1 megawatt station by around 2030 assembled in high orbit, then scaling up to 10 megawatts by the mid-2030s to prove real mass power is possible. And finally, targeted for around 2050, a full commercial station in orbit generating 2 gigawatts of power with a solar array and antenna around 1 kilometer wide. Each step is a giant leap, and every one of them has to succeed before the next becomes possible. But here is why this specific breakthrough matters so much despite all those caveats. For 50 years, the single hardest technical barrier, the thing that kept space solar power in the realm of fantasy, was the wireless transmission. The precise, efficient, long-distance beaming of power to moving targets. That was the wall. And China has now shown in a complete working system on the ground that the wall can be climbed. They have proven the core principle works. It is worth remembering that this is not only a Chinese dream. Space solar power is being pursued by the United States, by Japan, by the United Kingdom, and by others. It is a genuine global race. But the scale, the funding, and the long-term national commitment China is putting behind its version are remarkable, backed by a national plan that explicitly prioritizes the use of space resources. While some countries are still debating whether this is even feasible, China is building 75-meter towers and beaming power to drones. Step back and consider the sheer scale of the ambition. We are talking about building power plants in orbit, structures a kilometer wide, assembled by robots in the vacuum of space, catching the raw, unfiltered light of the sun and raining that energy back down to the planet below. This is the kind of mega project that once existed only in the pages of science fiction novels. And the reason it is worth taking seriously, rather than dismissing as a fantasy, is the prize at the end, a source of clean energy that never sleeps. No night, no clouds, no seasons, no limits imposed by the atmosphere. A continuous, round-the-clock river of power flowing down from orbit. If it can truly be built at scale, it would not just be another way of making electricity. It would be one of the most significant achievements in the history of energy. The sun has been pouring out more energy than our entire civilization could ever use every second for billions of years. We have simply never had a way to catch it all. Almost all of that energy sails past our planet and is lost to space. A solar power station in orbit is, in the end, an attempt to finally reach up and catch a piece of that endless river at its source before the sky ever gets in the way. For 50 years, it was a dream. On a tower in Xian, it just took one very real step toward becoming a machine. It makes you wonder what other pieces of old science fiction are quietly being turned into engineering right now, in labs most of us have never heard of. If you find his breakthroughs as fascinating as I do, subscribe, because there is far more of this story still to come, and the future is arriving faster than most people realize. And tell me what you think in the comments. Is space-based solar power the true future of clean energy, or is it too difficult, too expensive, and too far away to ever really work? The most thoughtful answer gets pinned.